Today will be a strange lecture because I will not explain quite a lot of things that I will show you. That is because you had neither the theory of relativity nor the theory of nuclear structure in your modules in chemistry. And so necessarily what we will have to do is introduce a lot of nuclear spin physics by analogy with something you know, namely the angular momentum theory. So to get us started, let us look at the difference between the theory of orbital angular momentum that you well know and the theory of spin that we are building in this module. So I'll make a little table here. So angular momentum on this side and nuclear spin on that one. And let's take a look at what the difference is. We know that because of the periodicity of three-dimensional space, orbital angular momentum is quantized, and the values it can take are integers. So here L was from the set of all integers. For the nuclear spin, because it is not something that is related just to spatial rotations, there are also relativistic boosts. We can have half integers, so S can be half integer. Orbital angular momentum cannot. Then the second difference is at ambient conditions in our terrestrial chemistry, angular momentum can change. If we excite an electron in an atom from an s orbital into a p orbital, its L quantum number changes, so can change. However, at typical conditions of chemistry experiments, the nearest nuclear excited state is inaccessible. It will be tens and hundreds kiloelectron volts away from the ground state. We do not have those energies in practice in chemical systems. So although technically a nuclear spin can be changed by exciting the nucleus, it does not happen in practice. So not in practice. And for the orbital angular momentum, we had full quantum mechanical theory. For the nuclear spin, we will have the approximations today. But one important thing that pertains to both is that angular momentum, because this is, say, an electron moving in a circle, a moving charge is a current means magnetic field, a loop of current means magnetic moment. So angular momentum can give rise to a magnetic moment, so-called orbital Zeeman interaction, and that is easily observed. And also here we have a magnetic moment, although the mechanics of the two are somewhat different. For the orbital angular momentum, we have full quantum mechanical theory that has been built to you in your angular momentum course. For the nuclear spin, we will have 2s+1 states that obey the superposition principle. So we can have arbitrary complex linear combinations of spin states, but beyond that we will be using the analogy with the orbital angular momentum. Okay, let us now try and build something. Let us take a spin half. It has two states, and we will simply pick ourselves a basis in a complex two-dimensional space that would have two orthogonal vectors. Now we have two states and we have their superpositions, so in general we will have a vector with two coefficients, c half and c minus 1/2, corresponding to the contribution to the superposition from the spin up state and the spin down state, and we simply express it as c half times 1, 0 plus c minus 1 half 0 1. These are our expansion coefficients, and that is our basis set in the complex two-dimensional space, and that's essentially the superposition principle. And then we have the usual observation from quantum mechanics that c half absolute squared plus c minus half absolute squared must be equal to 1. That is the balance of probabilities in quantum mechanics. Okay, so we have picked ourselves a basis, and in a lot of cases that would be denoted alpha and that would be denoted beta. Let us now try to build the same operators for spin as we had for the orbital angular momentum. Namely, we want the 3 Cartesian projections of the spin, and we want the total s squared in this basis. Well, let's think about what such matrices might look like. If we start with the s square, we know from that analogy that s squared acting on the alpha will be the value of the spin times the value of the spin plus 1 times the original function, or vector in this case. So 1 half plus 1 times alpha. Likewise for the beta. What does that mean for the corresponding vectors? Well, s squared as an operator must be a 2 by 2 matrix, and when it acts on 1 0, it must return us 1 0 multiplied by 3 quarters. So we have here 3 quarters and then 0. Then when we multiply the beta one, and I'll put it right next here, so like that, we must get 3 quarters and the same vector out. Right? So whatever this is, when it multiplies this vector, it must give us the same vector multiplied by 3 quarters. When it multiplies that vector, it must give us the same vector multiplied by 3 quarters. But of course, notice that this is a unit matrix, and so that s squared must therefore also be 3 quarters, 0, 0, 3 quarters, and that is our s squared. Okay, we did manage to build it without too much hassle. Let us think about sz. Likewise, whatever is here must act on 1 0 and then on 0 1, and for 1 0 it must return us the 1 half times 1 0, so 1 half 0. For 0 1 it must return us minus 1 half, again multiplied by the original vector. Same observation that that's a unit matrix, and therefore that original thing here is likewise 1 half minus 1 half, and that is sz. It will be somewhat more interesting for the x and the y. Let us start by building instead the raising and lowering operators. First, we know that s plus acting on the state beta produces the state alpha, so it raises it 1 click in the projection. However, we also know that when s plus acts on alpha, it must produce 0 because there's nowhere else to raise it. And likewise for the s minus, so you have covered that in your theory of angular momentum. And remember, for higher either spin or angular momentum quantum numbers, we had a big looking square root here, which will start to matter if we go to higher spins than half. Okay, let us think about what we must have here in order to raise our states. If we act on 1 0, we must have 0 0, because the top state cannot be raised any further. If we act on 0 1, that's the bottom state, we must have the top state out. And so that then is our raising operator, S plus. Then likewise for the lowering operator, it must drop the top state into the bottom one. So 1, 0 becomes 0, 1, and 0, 1 becomes 0, 0 because there's nowhere else to lower it. So same philosophy, and so that therefore is our lowering operator, S minus. But remember how we defined the S plus and the S minus. This was Sx plus I Sy, and that was Sx minus I Sy. So if I add that to this, just term by term, Sx plus Sx will be 2Sx, Sy will cancel because there is a minus in here, and we would have S plus plus S minus. So Sx is actually S plus plus S minus over 2. And Sy is S plus minus S minus over 2I. So from this, we conclude that Sx is S plus plus S minus over 2. And Sy is S plus minus S minus over 2I. Hats everywhere. Let us just then take the matrices we have here and take those linear combinations, and that will give us the Sx and the Sy operators. Sx, therefore, is a counter-diagonal matrix, 1/2, 1/2, and Sy will have S plus minus S minus over 2I, so 1 over 2I, and then S plus gives us an element in the corner, 1, and S minus gives us the element in the bottom corner, so -1 here. I will multiply both the numerator and the denominator by I. This will pop an I in the numerator and a minus in the denominator, and I will pull them both in. So 0 minus I over 2 plus I over 2, 0 is our Sy operator. Okay, it would seem that we have built it without too much difficulty. The way we proceed for higher spin nuclei, for example spin 1, is literally the same. We say, well, okay, mathematically, quite apart from any physics, if we have a triple state quantum dynamics, that's just a three-dimensional complex space with linear combinations allowed on it, and the certain eigenfunction, eigenvalue, and raising and lowering relations that are prescribed by our analogy with the angular momentum. So there we would make ourselves a 3-element vector. We would then go through the eigenvalues which we know, get ourselves a 3×3 matrix S squared, then 3×3 matrices for S plus and S minus, then take those linear combinations, and that's our three-dimensional representation of the same Lie algebra that describes spin. Okay, now you notice that I've just pronounced a scary word called Lie algebra. Sorry, chemists, you didn't have continuous group theory in your mathematics so far, but it's something you might want to look up, because the reason all these derivations appear so effortless is that there's a very rich mathematical structure behind spin, which we unfortunately do not cover. What particularly it leads to is that these matrix representations of our operators have exactly the same commutation relations as the angular momentum operators, which I've taken so much sweat to commute in the previous lecture. Let us actually verify this, and it would be a lot easier, of course, for 2×2 matrices than it had been for the differential operators that we have there. So let's check that. Sx, commutator Sy, would have been ISZ if we followed the analogy directly, but let's just check that that is in fact the case. Okay, Sx Sy minus Sy Sx, plugging in all the matrices. Sx is that 0, 1/2, 1/2, 0, Sy 0 minus I over 2, 0, minus same matrix over 2, I over 2, 0 times 0, 0, 1/2, 1/2. Okay, well, we hopefully haven't forgotten how to multiply matrices, so let us work through the exercise. We have that times that, it's I over 2. So I over 2. We have, so that's 0. And it's a 1/2 and a 1/2, so it's actually I over 4 here. Not forgetting the denominators. That times that is 0. That times that is minus I over 4. Then minus this times this, minus I over 4. Then that times that is 0. That times that is 0. And that times that is plus I over 4. Okay, subtracting out, we have I in front, then 1 over 2, 0, 0 minus 1 over 2. And that is, of course, I Sz as required by the commutation relations. And in the workshop, you will be asked to do the same for 3 by 3 matrices, and you will see that they follow the same commutation relations. This is because these operators, strictly mathematically speaking, are irreducible representations of a certain Lie algebra that describes spin, which is isomorphic to the Lie algebra that describes the angular momentum. And this is why this analogy works so well. Okay, that is our exploration of the operators. Notice that you will find in the literature another set of spin operators called Pauli matrices, and those are simply different from these by a constant factor. So you have sigma x defined in the literature as 0, 1, 1, 0, then sigma y is 0 minus I 0, and then sigma z is 1, 0, 0, minus 1. You can see why computer scientists would prefer this, because you've got zeros and ones essentially, and why magnetic resonance people would prefer those. This is because the structure relations, so all of these commutators, are particularly simple if you have halves here in the elements. If we started commuting Pauli matrices, then the commutator of sigma x and sigma y would produce sigma z with a numerical coefficient. And then if we go to higher dimensional irreducible representations, these coefficients would drift. And it is in practice actually rather inconvenient to use Pauli's original matrices. They were actually invented by Dirac, and they feature in Dirac's equation, and they feature like that. So don't be surprised when in the literature occasionally the names for those and those are used interchangeably as Pauli matrices or spin operator matrices. They have exactly the same nature, they come from the same place, it's just different branches of physics have different notational conventions for purely historical reasons. Okay, so these are our operators. You will see in the handout I have also given you an example of 3x3 operators for spin 1. We will not derive them here because it's essentially the same exercise, but they follow exactly the same commutation properties. One final thing to notice here is that multiplication properties do depend on dimension. So commutators are exactly the same no matter which spin you have, but be careful with the products because they do depend on which spin you have in there. And s squared, for example, sx squared for spin half would be different from sx squared for spin 1. One would be a multiple of a unit matrix and the other would not be. Okay, so that's the algebra. Let us now go through the magnetic moment. So item 2. Magnetic moment. Only electron does have a simple connection between the spin and the magnetic moment. It literally just follows from Dirac's equation. If you take Dirac's equation, put in the magnetic vector potential into it, eliminate the degrees of freedom that are responsible for the antimatter, mathematically, then after a couple of pages of dense mass you do get the magnetic moment for the electron. So electron magnetic moment follows directly, and there's a simple expression for it. So mu e, it's a vector operator, of course, and minus ge mu b, and then the spin operator vector. So this is a vector mu x, mu y, mu z, and that is a vector sx, sy, sz of 3 operators. That is the electron G factor, slightly bigger than 2 for very complicated reasons to do with quantum field theory, and mu b is Bohr magneton, just a bunch of fundamental constants which I have given to you in the handout. So for electron it is straightforward. For the nucleus, remember a few lectures ago we had the briefest glimpse into the nuclear structure theory, where we had some not terribly well-known retention potential, we had spin-orbit coupling, we had some not terribly well-known internucleon interactions, etc. So the theory of nuclear structure even today is not fully worked out. It is not possible to predict the fine details of structure, particularly of heavy nuclei. Thankfully, mathematics comes to the rescue, and if we again assume that we are purely and solely in the nuclear ground state, then there's a wonderful theorem in mathematics called Wigner-Eckert theorem that simply tells us that whatever is happening inside that nucleus, we don't particularly care. The magnetic moment has to be proportional to spin. So nice and easy. And therefore, for the nuclei, mu x or y or z operator is just gamma s x or y or z spin operator, where gamma is the empirically measured magnetogyric ratio, which even today on the biggest supercomputers, if we do nuclear structure properly theoretically, we cannot properly predict. Right? So empirically measured, and then that's the end of the story really, if we are honest about it. Fine, and then of course all of this interacts with the magnetic field. You all remember this lovely relation that we have from classical physics. It still holds, and then we just have the external magnetic field and these magnetic moments interacting. Then that becomes the Hamiltonian, and this is where our quantum mechanics is coming from. Occasionally people go through the full quantum field theory for the magnetic field as well, but this is really only necessary at very low temperatures, so Kelvin to millikelvin, and we will not consider the magnetic field quantum mechanically, only the spin. For us, the magnetic field in NMR spectroscopy is just a classical Maxwellian magnetic field, external vector, with which magnetic moments interact. Okay, how are we to put all of this into molecular quantum mechanics? You've seen it in those PowerPoint slides in my second lecture, how magnetic interactions enter quantum theory, where we previously had just the momentum, we get momentum minus QA, where Q is the charge and A is the vector potential. But at this level, we can take advantage of the fact that all of these interactions are exceedingly weak. They are not even joules, they are millijoules, on top of hundreds of kilojoules per mole of your standard electronic structure theory. You all remember the various ionization energies of common molecules like benzene and so on. They are in multiple electron volts, which translates to hundreds of kilojoules per mole. Energies in here are all very tiny, so 10 to the minus 5 to 10 to the minus 6 of that, and so we can use mathematicians' favorite trick. We can use the Tailor series. We can say, well, okay, we have our energy of the molecule, and it will be the function of some nuclear magnetic moment here, which will be a vector, and then the function of the external magnetic field. We do, however, know that these energies are exceedingly weak of these perturbations. And so, well, standard Tailor series, really. We have the energy that is there in the absence of nuclear magnetic moments and the magnetic fields, all of these Coulomb interactions and so on that you have there, plus first derivatives, d energy by d, for example, magnetic moment components x, y, z, and I will sum over them here, so times mu k. Yeah, so that is the first term in the Tailor series. We take the derivative of the energy with respect to the nuclear magnetic moment, evaluate it at the point when the nuclear magnetic moment is 0, doesn't exist, multiplied by z. That's the standard linear term in the Tailor series here. Plus exactly the same for the magnetic field. Sum over the three Cartesian components, dE by dBk, bk. Those are the linear terms. Then we will have all of the mixed terms. So the second derivative, d2e by d mu n d mu k. And the sum will now be the double sum over n and k. And I think there's a half in front in there as well. And then mu n mu k plus the same term for the magnetic field, half sum over n and k, d2e by dbn dbk bn bk, plus the mixed term when one of the derivatives is with respect to the nuclear magnetic moment and the other one with respect to the magnetic field. So a half here, and then nk d2e by d mu n, but dbk mu n bk, plus third and higher order terms, which are really too small for us to consider. Let us take a look at what we now have here. We are not terribly interested in magnetic resonance in this. That is just our unperturbed energy from any standard electronic structure theory package, Hartree-Fock, DFT, post-Hartree-Fock, whatever it is. Just talk to computational chemists and they'll be happy to provide that. Now, this is the interaction of the nuclear magnetic moment, right? So notice it's a sum, every component of that onto the components of some other vector. So this is the nuclear magnetic moment interacting with something else in the molecule. And of course, the only thing that the rest of the molecule has is other electrons. And then from those electrons, we know that they do have orbital angular momentum and the corresponding magnetic moment. So this is actually spin-orbit coupling of nuclear spin with the orbital magnetic moments of the electron, so SOC. not something that we realistically ever see in magnetic resonance, because in the liquids we have rapid tumbling, which averages this out, and in solids it ends up contributing to the chemical shielding. That is the interaction of whatever the molecule has with the magnetic field, and the molecule presumably has some magnetic moment coming from just the motion of the electrons, and so this is the orbital Zeeman interaction. Again, rarely practically seen in magnetic resonance except in the gas phase. This, however, is something that we see a lot. This is the interaction between the two nuclei, mediated potentially by the electronic structure theory. There are direct couplings between magnetic moments, just magnetic dipole interaction, just like any two bar magnets would attract or repel, but there are also contributions from electronic structure theory, so these are J couplings and dipole-dipole interactions. So J and D. And we will meet both in due course. This term is an interaction with the magnetic field twice, mediated by something in the electronic structure theory. This is polarizability. Now, the first instance of the magnetic field creates a magnetic moment in the molecule, which then interacts with the field itself. And in the magnetic case, the polarizability is called susceptibility. So this is magnetic susceptibility, denoted chi. And finally, we have nuclear spins interacting with the external magnetic field in some way that may be direct, right? So direct interaction like this of a magnetic moment with the field, but also there is a contribution from electronic structure theory, so this is chemical shielding. And this then is our Hamiltonian in magnetic resonance. We do not care for this. We assume the rest of the molecule to be in the ground state. We do not care for that except in the gas phase. We do not care for this. Susceptibility does not actually depend on the nuclear spin, and so we just package it away into E0 and not worry about this. The two important terms that we do worry about in magnetic resonance is that the chemical shielding and that all of the interactions. And this is what we will spend a lot of this module exploring. You will notice here that these are elements of vectors. This has two indices, so that is actually a matrix, and that is actually a matrix, and the chemical shielding in different directions would therefore be different, so it is anisotropic. Likewise, for the interactions, they are all directionally dependent, and so these anisotropies will play a significant role in things like protein structure determination with nuclear magnetic resonance, because the anisotropy of the dipole-dipole interaction is responsible for the nuclear Overhauser effect, which is used for interatomic distance determination in magnetic resonance. Okay, now the final question here is, how do we actually calculate all of these derivatives? Because, well, the energy here is a complicated beast, right? A lot of calculations. How does a computer, or whoever it is that does these calculations, actually do them? There's a lovely theorem for first derivatives called Hellman-Feynman theorem from our good friend Mr. Feynman, whose lectures you must have come across on YouTube somewhere, but essentially dE by d whatever parameter alpha at the ground state is the wave function of that ground state, then the derivative of the Hamiltonian with respect to that parameter times the wave function of the ground state. I will not prove this theorem. The proof is a bit lengthy and technical, but We know what the Hamiltonians are. They're usually actually quite simple. And if they have some parameter, like a magnetic field, in this case, it will be entering through the vector potential. We can easily differentiate the Hamiltonian, get whatever other operator that comes out, and then do the expectation value. The expression for the second derivative is slightly more complicated, but also merits discussion. If we have two parameters, alpha and beta, in our Hamiltonian, there will be two terms. There will be the ground state term, psi, and then the second derivative, so h double prime alpha beta. I will not use this notation for compactness sake. So, and then psi, plus a sum over all of the excited states. So for k that's greater than 0, so we do not account for the ground state in this sum. And then something that looks close to perturbation theory, if you've ever seen it to second order, but it really isn't perturbation theory. These expressions are exact. Then we have psi, and then h prime with respect to alpha, and then psi k excited state, and then psi k excited state again, h prime with respect to beta, and then the ground state here. And that is the energy of the ground state minus the energy of the excitation. Plus here the complex conjugate of this bunch of brackets. Now, the complication here, notice, is that we have a sum over all of the excited states. And this is something that computational chemists will complain bitterly about if you ask them to calculate the chemical shielding or the J coupling for you, because typically ground state properties, like that one, are easily computed with density functional theory because it is built on top of the ground state electron density. Excited states, however, are badly done within DFT and seriously difficult even within post-Hartree Fock. So the complexity here goes as n to the 7th, n to the 9th with the number of electrons in the system, so really steeply. And so the second order response properties, they are called, like J coupling, are actually pretty difficult to calculate, although modern quantum chemistry packages are actually quite reasonable, unless you are dealing with d elements or some serious transition states where the electronic structure theory is not necessarily in the ground state. Okay, the final thing to cover is, after the dust settles on those and those, it turns out that there are only 3 mathematically distinct types of interactions in magnetic resonance. The physical nature of those interactions can of course be pretty rich, but at the end of the day, once you write them down as the Hamiltonian, there are only 3 types that are distinct from the mathematical point of view. If you look at the Tailor series above, you will see that there are spin interactions which are linear in the magnetic moment, like that spin orbit term, or like this chemical shielding, right? It's just this mu. There are terms that are bilinear, so they are linear in one spin and linear in the other. And there are terms which are quadratic, in this case in the magnetic field, but there are various indirect interactions that look as if the spin is interacting with itself. So the third topic for today is algebraic interaction types, or classification. Okay, first type, linear. For example, shielding. if we look at the interaction of the spin with the magnetic field, there are the three components of the magnetic moment proportional to spin. There are three components of the magnetic field, and there's some matrix. If we write that out as a Hamiltonian, this is called Zeeman interaction, Hz, and it literally has the spin vector, then a 3×3 matrix in between, and then the external magnetic field vector. And if we separate this out into components, it looks like this. It's the row vector, Sx, Sy, Sz. Then there is a 3×3 matrix, Axx, Axy, Axz, Ayx, Ayy, Ayz, then Azx, Azy, and Azz, with the magnetic field Bx, By, Bz. And this is called linear because it is linear in spin operators. If we have several spins, we will have sums here, and this magnetic field will of course be the same, and then different spins can have different. This is called the shielding tensor. There are different notational conventions here. Physicists like to measure chemical shielding relative to bare nucleus in vacuum. Chemists like to measure it relative to TMS or some standard substance. For physicists, it's called chemical shielding because it's literally relative to bare nucleus. For chemists, it's called chemical shift because it's a shift from tetramethylsilane, and the signs are different as well. So there's a minus sign between the physicists and the chemists' convention. Okay, these are linear interactions, then be bilinear. And that is every spin-spin coupling you'll ever meet. For example, dipole-dipole interaction, you will have HDD. We'll have a pretty complicated matrix in between, but there will be the first spin vector, then the interaction matrix, then the second spin vector. And exactly like this, you will have the spin operator on the first spin in a triad like that, then a 3×3 matrix. I will not rewrite the components, and here S2x, S2y, and S2z. And that's it. And we will learn to make operators which are specific to a particular spin in the next lecture. Now, there is a bastard third type which actually didn't come out of there. That is because it comes out of details again of nuclear structure theory, where different nuclear spin orbitals have different charge distribution. And so electrostatic interactions of those charges, because they split nuclear spin orbitals, they manifest as spin interactions, right? So although they begin their lives as electric, they end up looking magnetic, and these are quadratic interactions. There are only two types. For electrons, it's called zero-field splitting. For nuclei, it's called nuclear quadrupolar interaction. This is because the quadrupole moment of the nucleus, so nuclei are not spherical, so they have electric quadrupole moments, those with the spins greater than half. And that electrical interaction looks in magnetic resonance like a spin interaction. So quadrupolar coupling is the same spin turning up on either side of yet another 3×3 matrix. So mathematically this looks like a spin is interacting with itself, but this is only the effective picture because we are not considering the full nuclear structure theory. And we will not cover them in this module because they're seriously complicated and only really consequential in solid state. Okay. The summary of the lecture we don't know much about nuclear spin necessarily because we are chemists. If you ask the physicists, they pretend that they do, but they also really don't. And so we have to build all of our formalism by analogy with the orbital angular momentum, and this is the way it has historically been done, and is in fact quite a successful approach so long as we remember the various limitations of it. So we take all of the relations that we knew for the orbital angular momentum, we follow the same recipes, and it turns out without too much difficulty we obtain the matrices that behave exactly like the operators that we would like in these discrete spaces pertaining to spin. We've built those matrices. We then asked, okay, how can we in practice pull out the spin interactions from what is actually a fairly complicated molecule where a lot is going on? The answer is to assume that the rest of the molecule is in the ground state and only consider the very weak interactions pertaining to spin and the magnetic field. Then the Tailor series, just straightforward multivariate Tailor expansion, gets you a bunch of terms which do have physical meaning and depend on the derivatives of the energy. This is how you calculate the derivatives of the energy. Catch your nearest computational chemist and shake them until they calculate this for you. And for us in magnetic resonance, it boils down to only three mathematical types of interactions. You have things that have spin operators once, so they are linear, different spin operators twice, and so they are bilinear, and the same spin operator set twice, and those are called quadratic, and we will only look at that and that in our liquid state magnetic resonance module here. Any questions?